Okay, off we go. So, let's see here. Attendance code, attendance quiz, and all that. Time's clicking. So last time, here's what we just concluded. We concluded this statement right here. It's sort of a physical interpretation of a vector line integral. Let me just remind you, this expression right here, it's called a vector line integral. Our motivating application for this construction was we were interested in computing work. Right? How much work does it take to move along a non-straight curve, right? While applying a non-constant force, and how do you deal with that? And so the only interpretation we have so far, therefore, is work. How do you compute work? So what we entertained last time was, okay, if this vector field here, if that vector field were to represent a fluid flow instead of a force, what does this compute? Right? The answer we got was a little bit weird. The first thing to say about the answer is that it depends on your cross-sectional area. If you have a bigger cross-sectional area, let me remind you up here, the idea of the cross-sectional area is it defines what fluid are we keeping track of. And in particular, what we're interested in is that fluid that we're keeping track of, to what extent is it flowing along the curve? Well, more fluid, of course, would mean more fluid flowing along the curve. So, no surprise that our answer is proportional to area, and because it's proportional to area, and sort of obviously so, it really makes more sense to talk about how much per unit area. Right? And so here's an analogy. If I were to ask the question, how much does iron weigh? Okay, well, I guess we would describe the weight of iron with a force, but wait a minute, how much iron are you talking about? And, well, of course it's going to be proportional to the volume of iron. So when we talk about how much iron weighs, we don't talk about the force, we talk about force per unit volume. Right? Does that make sense to everybody? So same thing here. Doesn't make sense to talk about the rate on its own. We'll talk about the rate per unit area. Okay. All right. So that aside, our nice sort of punchline is that the interpretation we have of the vector line integral is it represents to what extent is the fluid flowing along the curve. And I think that's fairly pithy and compact, and it's a new concept to kind of get used to. But here's a couple of examples. Okay. So the examples are considering a special case. The special case is that we are looking now at a closed curve. Closed means that it starts and ends at the same point. Kind of like, for example, there you go, that's a closed curve. Right? Does everybody see what we're talking about? Starts and ends at the same place. Okay. All right, so when you're talking about a closed curve, what does a line integral represent? Well, okay, it still represents the extent to which the fluid, I'm going to use green for the fluid, to what extent is the fluid flowing along the curve? And if we look at this first example, well, let's think about this one little bit at a time. Along this little piece of curve here, to what extent is the fluid flowing like so? To what extent is that fluid flowing along the curve? Well, golly, quite a bit. It's flowing entirely along the curve. And furthermore, as you go around the curve, the fluid is going along the curve around with the curve. So, what would we expect this line integral to be? What would I anticipate about this line integral? Well, I'm going to get positive flow along the curve there, and positive here, and positive everywhere around the entire curve. We would expect a positive line integral because the fluid is literally very much, almost exactly even, going around the curve. Okay. All right, so the terminology that we use to describe this, as a result kind of that picture, is the term circulation. I think it's a reasonable thing. In particular, if you notice, because this is a closed curve, closed curves, because it has to come back to where it was. If you look at the unit tangent vectors, Forget about the curve itself. You just look at the unit tangent vectors that, as you go around the curve, the unit tangent vector has to make a complete circle as you go around the curve. And this line integral is measuring the extent to which the fluid is kind of doing the same thing. So circulation, I think, is a pretty natural reference to the fact that those tangent vectors are going around in a circle. Anyway, it's just a term. How are we doing so far? Everybody with me? Okay, now let's see another example here. Let's see here. We're going to look at the same vector field, you'll notice, and a very closely related curve. But you'll notice this time the curve is going the other direction. It has the opposite orientation. So now let's think about, okay, what's the circulation here? What is this lineup? To what extent is this fluid flowing along that curve? Well, again, it's the same fluid. And let's look one little bit at a time, just like we did before, et cetera, et cetera. And let's see here. Well, along in there, the fluid is going this way. The curve, though, is going the opposite way now. The new curve, different curve, oriented the other direction. To what extent is the fluid flowing along the curve? Well, it's kind of going the exact opposite of the direction of the curve. So I would say negative there, because it's the opposite. And then likewise, to what extent is the fluid flowing along the curve along in there? Well, again, negative. It's going the opposite direction. And adding that up over the entire curve, reasonable to expect this would be a negative circulation. Is that cool? Anybody's with? Now, I will point out one thing here. This is a little bit counterintuitive. If you notice, these two pictures, these two cases we were just looking at, it's the same fluid. Exact same vector field, exact same integrand. If it's the same fluid, how come for one of them the circulation's positive and for the other one it's negative? It doesn't seem right. Yeah, same fluid, why wouldn't it be the same circulation? And the answer is, when you're computing circulation, you're looking at the extent to which the fluid is flowing along the curve. The curve is a reference. We're not looking at the fluid by itself. We're comparing how the fluid is flowing compared to how the curve is moving. And that's the big difference. It is indeed the same curve, the same fluid, but it's the opposite curve. Opposite orientations. So you might say these two different circulations, they're asking about the same fluid, but they're asking opposite questions. The first question on the left here says, to what extent is the fluid circulating counterclockwise? Answer, a positive amount counterclockwise because it's counterclockwise. And the second is saying, hey, to what extent is this fluid circulating clockwise? Because that's what the curve's doing. And, well, to what extent is this flowing clockwise? I would say a negative amount clockwise because it's still counterclockwise. Does that make sense? Is everybody happy with that? All right. Okay, so last example we'll see here. We'll look at this here. And this is a confusing one. It's not readily apparent like the first two what the answer is here, because you're going to notice kind of on the left side of the curve here, the fluid is flowing that way, the curve is going that way. We would sort of expect to pick up negative terms along the left side of the curve. But you would expect to be picking up positive terms along the right side of the curve. Hey, what's going on here? There's conflicting quantities. It's hard to tell. And you can speculate, kind of eyeballing, maybe trying to get a sense, which of these opposing forces will sort of outweigh the other, but still it's not obvious and we're kind of speculating. Side note, we're going to have a much better way to answer this question, probably not quite today, but we're going to almost get there today, and then on Wednesday we're going to have a fabulous way to answer this question that's much more direct. Okay. All right, last point of view I want to give you about circulation. I think this is nice. This serves some helpful purposes for sort of physical and geometric interpretation. And this is just a take. Right? This is just a point of view. But if I look at something floating in the fluid. So again, keep in mind we've got a two-dimensional fluid here. I like to think of this as maybe the surface of like a little creek or river or something like that. And we're looking at fluid flowing as indicated by these arrows. Imagine if I had a little leaf, fall colors and everything, right? This little leaf floating along this river. And now just intuitively speaking, I mean, what would you expect if you drop a leaf at that point and the water is doing what the arrows suggest? What's going to happen to that leaf? And I propose that leaf would be rotating. Right? If the water is flowing around kind of like that, wouldn't you imagine the leaf would be rotating? Does that make sense? Seem believable? I don't know if y'all have ever had this little pleasure, but sometimes you're lucky. You're looking down at a little creek or rivulet or whatever, and there's a little eddy current, a little whirlpool kind of thing, right? And when I was a kid, I used to like take a twig and kind of drop it on there and then watch it spin real fast. So that's what I'm talking about, right? That's kind of sort of what this fluid that I have indicated by this vector field is representing. And so again, I claim that leaf would start rotating counterclockwise. So that said, I like to think of the closed curve as proposing the question, hey, how much would the leaf, whose boundary this curve is, how much would this leaf be rotating counterclockwise? And that the line integral then is the answer, positive amount counterclockwise. So this leaf would be rotating counterclockwise. That make sense? All right. Cool. All right. So moving along. Let's just go back to thinking about vector line integrals as mathematical objects and how to compute them. And sometimes you get lucky. Y'all remember I'm an enormous fan of the idea of using symmetry arguments, right? Odd symmetry arguments are fabulous. And again, 20% of the integrals conservatively estimated that I had to deal with as an undergraduate. Integral zero by symmetry, right? Totally awesome. This is another one of these things, kind of along similar lines. Every so often you get lucky with the geometry. So here's an example. We've got a curve. Let's see here. We've got a curve, and it's, I'm going to say parametrized by these equations. It's a little bit of an abuse of the term parametrized. A parametrization is rectangular position as a function of time. That's not what's explicitly given here. But since I've given you spherical coordinates, we have conversion formulas. You can plug into those conversion formulas, and we're a hop, skip, and a jump away from having literally rectangular coordinates x, y, z as functions of t. Right? So I'm going to loosely, casually speaking, call this a parametrization of some curve. And it'd be a nightmare of a curve because, after all, when you plug in for x, y, and z, you're looking at sines and cosines of phi and theta, and so we're going to have sines and cosines of these ugly expressions. It's going to be an ugly expression. Okay, but except for one thing, and you'll notice quickly, the entire curve satisfies rho equals 1, which means the entire curve is on the unit sphere. And so however weird that curve may be, it is entirely on the surface, what you might call the surface of the earth there, if you're just looking for a metaphor. We're moving along the surface of that sphere. And exactly what is it doing on the sphere? Oh my gosh. Oh, wow, hard. Don't worry about that. I don't know. It's too much. Yeah, everybody happy so far? Okay, next observation. Well, let me finish this observation real quick. If I am moving along the surface of the sphere, then my tangent vector is parallel to the surface of the sphere. That's a geometric argument, something you got to just sort of think about, right? If you're walking along the surface of the Earth, your velocity doesn't have any upward component to it, right? If you're walking along the surface, your velocity is tangent to the surface. Okay, next observation. Let's look at our vector field here, the thing that we're supposed to be computing the line integral of. This vector field, well, it's hard to say. It's got a weird formula there. But notice, it is a scalar multiple of your position vector. Right? X squared y, whatever, it's some function, but it is a scalar. So this vector field always points in the same direction, plus or minus, but same direction as the position vector. And now let's look at the geometry here. The position vector, if you're talking about, as we are, rho equals 1, a sphere centered at the origin, geometric appeal, spheres have this wonderful property that their position vector is always perpendicular to the surface. That's sort of a peculiarity of spheres centered at the origin. And again, geometric appeal, something to think about that geometrically, persuade yourself that makes sense. So F, our vector field, being a scalar multiple of that, is always parallel to that and therefore also perpendicular to the surface. How we doing? Everybody happy? So I claim it's all over but the shouting at this point. We've got dr is always parallel to the sphere, and we've got F is always perpendicular to the sphere. So F dot dr, this dot product, well, those vectors are perpendicular, so that dot product is always 0. And that means that our integral is 0. We're done, we walk away. Didn't have to deal with the ugly parameterization. Didn't have to pull back through that ugly parameterization. Didn't have to do any integrals, right? Just clever observation and celebrate. What do you think? Isn't that nice? Okay. So, reasonable question that might come up. How often would we get this lucky, right? This is a carefully crafted example, right? I tailored this example so it would work out. And you might think to yourself, okay, well, yeah, but in the real world, come on, what are the odds? It turns out the odds are actually quite good. When we study physics and engineering, we tend to study natural things. And natural things tend to include natural shapes. Spheres come up a lot. Right? Vector fields that are radial come up a lot. This is not that rare. Right? So this kind of thing where the geometry just, oh my gosh, look at that, its answer is 0. Definitely worth paying attention for, and I'm not prepared to give any sort of numerical estimates of how often, but it's definitely enough that it's worth your time to keep an open eye. Is that cool? Any questions about any of that? Okay. All right. Okay. All right. This next thing is largely a matter of notation. The notation is really not that big a deal, but r prime, of course, you can write out in coordinates. You can distribute the dt. Pretty reasonable that x prime dt we might ought to call dx. Seems like a reasonable choice. And so what we have for our first time now, we have a coordinate representation of our vector differential dr for vector line integrals. So what we do with this, now this is just notation, but that dr, again, I can write it out in coordinates, dx, dy, dz. Our vector field will have coordinates. Let's call them p, q, and r, which, by the way, is a pretty common choice, whatever that's worth. Weird, but it's a common choice. And now I can explicitly write out this dot product, right? When you have a dot and you dotting two things whose coordinates you can write down, well, that's how a dot product works, and you can write it out like that. So, again, this is just notation, but this then is an alternative notation for writing a vector line integral. Now, why would you want to do such a thing? And at a casual glance, it's hard to make the case. We kind of like this notation over here. It's compact. It's physically relatable. The vector field is a natural physical thing. dr represents displacement. That's a natural geometric thing. Everything on the left kind of makes sense physically. And then if you look over to the right, what is Q by itself? Okay, look, I can answer the question. Here it is. Look there. Q is the second coordinate of your field vector. Maybe the field is force, so it's the second coordinate of the force, perhaps. But coordinates depend on bases, and bases are arbitrary. Right? So it's not what I would call a natural thing. So I think this notation on the right, based on at least how we're looking at it here, is clunky, bulky, and unintuitive. So I know I'm not making a very good case for this notation. So let me give you two reasons why you should care about this notation. The first is kind of philosophical, but beyond this course, it turns out that this notation is extremely powerful. It's totally awesome. There's things that you can do with what I'm going to loosely call this notation. What I really mean is the more general construction of differential forms. This is what we're seeing here with this notation is kind of a first example. This is an integral of what we call a differential one form. What does that mean and why do we care? Deep water, long discussion, not really appropriate to this class. But anyway, punchline is very hard to see it coming, but this is ultimately, in fact, very natural, just in a different way, and ultimately extremely powerful. And there are questions that came up in vector calculus in the 1800s that didn't get answered until the mid-1900s. Very difficult, very sophisticated questions. Questions that stumped Gauss, right? Didn't get figured out until, less than 100 years ago. And as I like to say, the person that, as I understand it, was most responsible for figuring this out, I personally am 2 degrees of separation from that guy. It's pretty cool, right? I knew someone who knew that guy, right? So it's very recent. He had a driver's license, for crying out loud, right? I mean, this is very modern math. So anyway, that's worth knowing. Again, if only sort of historical, kind of philosophical reasons. Now, the other reason you need to know is that this notation, whether for our Math219 purposes, for your future engineering purposes, you might not have any particular need to use this notation, but what you will need is to understand what to do with it when you see it, because other people like to use it. Whether or not they're making use of the powerful, tools of differential forms. So when you see this, what should you do? And here's what I propose. When you see something that looks like this, remind yourself that the dx, dy, and dz, that's just code for dr. That's just a reminder. It's just a different way of writing, hey, by the way, this is a vector line integral. And then related, what you might call the integrands here, that is the vector field. P, Q, and R are the coordinates of the vector field whose vector line integral that represents. So every time in an application, a physical application, something like that, every time I see one of these, I think, okay, all right, so they're using differential forms. Fine. What they're talking about, though, is a vector line integral, like so. Does that make sense? That's what I encourage you to do when you see one of these. Okay. All right. Moving along. Symmetry theorems. Now, I suspect that this is going to come as no surprise. We have an odd symmetry theorem. We've seen several previous odd symmetry theorems, right? If you have a symmetric domain and an odd integrand, both conditions being satisfied using the same line for each, then that integral is zero by symmetry. We've seen this for single variable integrals, we've seen it for double integrals, we've seen it for triple integrals, and now we're seeing it for scalar line integrals. So, odd symmetry theorem number 4. You're going to notice I've laid it out on the page in exactly the same way that we laid it out for the previous theorems. And again, just to emphasize how it's the same exact idea, same intuition, right? So hopefully pretty believable. Everybody okay with that? Everybody happy? Okay. There is an asterisk on this. This is for scalar line integrals, and it is only for scalar line integrals. This does not work for vector line integrals. If you're looking at a vector line integral, no such luck. There is no odd symmetry theorem for vector line integrals. It doesn't hold. It doesn't work. And I can argue pretty directly why it doesn't work. If you write down the expression for a vector line integral, right, so here it is, a vector line integral, and let's rewrite it like this. You may recall this is one of the alternative notations for vector line integrals. We don't really use it very much. I don't know. A lot of people love it. A lot of people use this all the time. I just don't tend to use it very much myself. I prefer this one in most cases. But anyway, in this form, you can kind of see part of why, part of the argument for why scalar line integrals work is, well, that little ds and this little ds, right, little mirror image, little chunks of the domain, they have the same size, and so you can imagine that, this is, the ds agrees on both sides, and then you get a minus sign from the oddness. You see how the cancellation would work. But because this is a vector line integral, we also have to look at the t vector. And if you look at the corresponding t vectors here, these unit tangent vectors, they're not the same. The ds's are the same. The t vectors are different. And they're worse than different. They're not the same, and they're not negatives of each other either. They're just different. Does that make sense to everybody? So crash and burn, right? We're not going to get cancellation because what we're actually looking at on these two different sides are just not related enough for this to work out. So yeah, no odd symmetry theorem for vector line integrals. Do be very careful about this. I mentioned before that symmetry theorems are wonderful and powerful and totally awesome, and I love them, but they are dangerous, right? They are delicate, and you have to be careful not to apply them when they don't apply. And this is another kind of, therefore, sort of a landmine situation. You got to be super careful not to, I forgot, and accidentally apply this to a vector line integral, because that's nonsense. Okay, so heads up, right? Be careful with that. Everybody all right? Moving along? Okay. All right, so that's 6.1. 6.2 is going to be our first example of what I'm going to call a really big theorem in vector calculus. It's going to be called Green's theorem. We'll see it in a couple. Well, not today. We'll see it. We'll finally get to it early on Wednesday. But this is going to be our first, in a sense, big theorem of vector calculus. And there are several big theorems of vector calculus, depending on how you count, 5 or 6 or 7, depending on this and that. And it turns out that they all have a lot in common. in very powerful ways. They're all in different geometric contexts, but they all have, a lot in common. So there is a particular point of view that I found to be extremely helpful when I was learning this material when I was y'all's age. Right? And I'm going to try to present all these theorems from this point of view that, again, I found to be just immensely helpful, and it's been my feeling ever since. And to make sense out of this, I have to explain kind of an abstract idea. And so I'm going to describe a sequence of thoughts, kind of a structure of argument, and it's going to seem kind of abstract. But then once we start to see actual explicit examples, go back through this again, and you'll see what I'm talking about. And I think this will all make sense in the long run. But anyway, I want to give you a first pass through these ideas before we see the examples, and then as we go through and do examples, again, come back and you'll see what I mean. Okay. So first of all, I'm going to define what do we mean by a quantity on areas. This is actually no big deal. A quantity on areas just says if you give me an area, namely a two-dimensional region, asterisk, we've got to worry about certain regularities. Let's not go down into the weeds on that. So just think a nice, normal, pretty two-dimensional region like that. If you give me a two-dimensional region, then there is a corresponding value describing what the quantity is on that region. So, no big deal. A couple of easy examples. A quantity called mass. You give me a region, I can ask, okay, how much mass is in that region? You give me a different region, we get a different amount of mass. Bigger region, probably more mass. Smaller region, probably less mass. But you give me a region, there's a corresponding mass. You see what I'm talking about? No big deal, right? Here's another one, another quantity giving values on regions, and that is area. You give me a region, we can talk about the area of that. Here's another one. You give me a region, we can talk about what is the perimeter of that region. Right? You give me a region, I give you a perimeter. Okay. Next idea. Now, we've talked about this before, but I've been kind of hand-wavy about it before. Here I want to make it just a little bit more precise. This is the idea of an accumulating quantity. Specifically, a quantity that accumulates over areas. And all I've told you about this in the past is this phrase right here, the whole is the sum of the parts. Right? So every time we did an integral, and I say I want to compute the total mass of whatever thing we're looking at. The total mass, how about this? I'll chop it up into little pieces. Each little piece has a mass, and the mass of the whole is the sum of the masses of the little parts. Right? Accumulating quantity. That's all we're talking about here. And the way I'm going to rephrase that is that disjoint unions add. So if you have, in particular, so here's a disjoint union, R1 and R2. Oh, I wanted a different color here. R1 and R2. They don't overlap. Right? But if I look at their union, right, the union is kind of the, let's see, how am I going to do this? Let me do this with a pencil. If I look at their union, and if I ask, well, how much mass is there in the union? Well, I'm just claiming that the mass in that disjoint union is the sum of the mass on the left plus the mass on the right. Again, it's just saying the whole is the sum of the parts. You know? So, every integral we've ever written down is appropriately interpreted the computation of an accumulating quantity. That's what an integral is. An integral is, we're going to break it up into little pieces and add up whatever we're interested in on each of those pieces. It's literally chopping into little pieces and adding up. All right, so accumulating quantities. Now we've computed masses and areas with integrals, capitalizing on the fact that these are accumulating quantities. And one thing you might notice, one thing we have never done and cannot do, I cannot use a double integral to compute a perimeter because perimeter is not an accumulating quantity. Perimeters just don't work that way. The perimeter of the whole just isn't the sum of the perimeters of the parts. An easy counterexample, let's look at the perimeter of this kind of left side, the perimeter of R1 here. And then we can look at the perimeter of R2, the perimeter of sort of the right side here. And we can look at the perimeter of that union. And is green plus blue equal to purple? Nope. Right? Just doesn't work. So perimeter is not an accumulating quantity. Everybody see what I mean there? So the purpose of this example here is to point out that having this feature of being an accumulating quantity is something to be appreciated. This is a valuable feature. This says if once you identify that you've got a quantity that's an accumulating quantity, well, you've got a potential avenue for how to compute that. You can use an integral. You can break it up into little pieces, deal with it on the little pieces, and then take it from there. That's an avenue that's simply not on the table for a non-accumulating quantity. So we got to appreciate accumulations when we see them. Everybody good with that? All right. Now this next part is a little weird. It's a point of view. It's a way of thinking about things. I find this to be very helpful, and please come along for the ride here. I think you're going to find this to be, in the long run, eventually I think you're going to find this to be a useful bit of intuition. I claim that all accumulating quantities can be thought of. I emphasize can be. You don't have to. And just in your mind, this is just a way to think about things. I'm not saying this is actually the case. I'm not saying that this is physically true. But you can pretend, you can think of accumulating quantities as behaving like a substance. Like a stuff of some sort that's distributed over the area in question. Now again, you don't have to. And very often, that's just not the way we would normally think about such things. So for example, here's an example. Let's look at this picture I have over here on the left. I think this looks like the bottom of a backyard swimming pool kind of thing, right? And let's suppose that the pool got drained for whatever reason, and there's algae growing on the bottom. Somebody forgot to put the chlorine in, something like that, and someone's going to have to get down there with a toothbrush and clean the whole bottom of the pool. It's going to take forever. It's going to take a lot of work to clean the bottom of the whole pool, right? Okay, work is not a substance, right? But you could, weird, you might want to, but if you wanted to, you could think of it as being a kind of a substance. And the grand total amount of work that's on the bottom of the pool, well, I can think of that as stuff distributed across the pool. I can think of some of that stuff as being in this little tiny little region, this little region D. And if I ask how much of this imaginary substance is there in that little tiny little region D, the answer to my question is going to be, well, how much work would it take to clean that little region D? And that's how much of this imaginary stuff I'm going to imagine as being in that region. So if you imagine it as being a substance, let's think of what would be the consequences of viewing work, for example, as being a substance. The consequence would be that, then I would be able to compute work by counting how much of that substance there is in each piece and adding up. In other words, The consequence would be that I could compute work by chopping it up into little pieces and arguing that the whole is the sum of the parts. Which it is. Because work is an accumulating quantity. Right? So this is a make-believe, again, highly voluntary, you don't have to do it, but it's a make-believe that leads you in the right direction, that will allow you a point of view of how to think about how to compute something that might not be true, but it'll always lead you toward valid arguments. It'll always lead you toward a reasonable computation. So anyway, it's a little bit weird, but ultimately I think that's going to be really helpful, really natural. Here's the next step. Let's talk about densities. And we've talked about mass density previously. You probably saw mass density for the first time in middle school or something, right? Mass per unit volume. Right? And I argued back in chapter 5 that, but you can, if the mass is distributed, let's say across an area, you could think of it as mass per unit area. And in general, you can just think per unit size, whatever is the appropriate notion of size for how your mass is distributed. Right? And what is the purpose of mass per unit size, mass per unit area in this case? Well, the purpose is that that's the thing that you multiply by area to get mass. Well, that's what it does. That's the whole reason that we would entertain mass per unit area, is so that we can multiply by area to get mass. And we've used this for other kinds of quantities. So we've talked about population density. Same basic idea, right? Different accumulating quantity, but it's still quantity per unit size, quantity per unit area, and that is still the thing that you multiply by area to get quantity, right? If you know the population density of Durham, right, and you multiply by the area of Durham, then you get the population of Durham, right? Is that cool? Is everybody with me? All right. So now, reminder: while you don't have to, you can think of any accumulating quantity as kind of like a physical stuff, kind of like a substance. And so, check out this little weirdness. We can talk about the idea of work density. Seems weird. What do you mean density? Doesn't work then have to be a kind of a stuff? Well, yeah. I'm thinking of it as a stuff because it's an accumulating quantity. And from that point of view then, what do I mean by work density? Well, I mean, look at small little pieces of area, and how much work does it take divided by what that area is, and that is what you would multiply times area to get work. Same idea for the other densities that we're more familiar with. Is all right? Everybody on board? A little weird, right? Okay. So I'm just going to take this now to the next sort of natural next moment. Here is a calculation that we did early chapter 5. Big yawn at this point. We've known for a while now that mass is an integral of density. Let's break this down and do a two-step observation. First of all, mass is an accumulating quantity because mass is the sum of the parts. Right? The whole is the sum of the parts. And then secondly, on any given little piece, mass is density times size. So two-step process. There's this key fact of mass being an accumulating quantity, and there's this other key fact that there's an associated notion of a density that comes as a consequence of it being an accumulating quantity. And again, big yawn, right? That's from early chapter 5. No big deal. And where it gets weird is when we think, okay, yeah, but I can take all of these ideas and I can do the same thing for work. This non-physical, non-concrete anyway stuff, the whole is the sum of the parts. And on any given little piece, the quantity, this accumulating quantity, is quantity per unit area times area. And so there is this idea, this general idea, whenever you have any accumulating quantity, you can make an argument like this. Right? And I would make the case that in some reasonable sense or another, all integrals can be thought of as, we have an accumulating quantity and the integrand is the associated density. Okay, that's very abstract, I know. Pretty abstract. By the way, we're going to write down a bunch of theorems that are kind of like this. Let me highlight this one. We're going to write down a bunch of theorems that are kind of like this, and at different times, depending on what seems reasonable to me at the time, sometimes I call these accumulation theorems because they are fundamentally about accumulating quantities. Literally, constantly saying the whole is the sum of the parts. And sometimes, again, depending on the context, I think of these as density theorems because in all of these cases, the integrand can and usually should be thought of as some associated density. Okay. All right. So I want to emphasize this is all very abstract, right? This abstract idea of a quantity, of accumulation, thinking of it as being a physical stuff. This is very abstract. For the moment, I encourage chewing on this idea of thinking of work, right, as being a kind of a stuff in the sense that it behaves like a stuff, right? And therefore, it being reasonable to talk about its associated density. This is going to be already a lot to start sort of digesting. And then we're going to do some weirder ones on Wednesday with powerful punchlines. Okay. All right, last little quick observation, and let's see here. Anyway, we'll see what we can do. Everything I was just saying was about areas, quantities just defined on areas. You can do the same for quantities defined on lengths or quantities defined on volumes, right? Same sort of thing. Over volumes, you can argue that the whole is the sum of the parts. For any accumulating quantity, that's the big idea of an accumulating quantity. And then, again, stuff is stuff per unit volume times volume. So, same basic ideas. Okay. Now we're going to talk about a particular, special, two-dimensional accumulating quantity. It's very unexpected. In order to be able to do this, I am going to have to set up a little bit of convention. I'm sure y'all are previously aware of the term boundary, right? If you have some region, the boundary is kind of that's the border between where the set is and where the set isn't, right? Boundary, it's just the edge, it's the border. Not a deep idea, but we're going to tweak this. Henceforth, boundary will be an oriented thing, oriented according to a certain convention. And this is going to be consistently now through the rest of chapter 6 and the rest of chapter 7. Boundary now means oriented according to a certain convention. There's a collection of different conventions. Here's the first one, and that is if you're talking about a region, if you're talking about a region D, some two-dimensional region, I like to think of this as a grassy field. And if you're interested in the boundary curve, okay, so for example, there's the boundary. That's the edge of our little grassy field. There's that key word boundary. Boundary now means oriented. Oriented how? Oriented in which direction? Which direction do I go? What's the positive direction along this boundary curve? And the answer, coded into the word boundary is go whichever way you have to along the boundary so that the region is on your left. It's an arbitrary convention. 150 years ago, if someone had decided differently, fine. Wouldn't have mattered. Right? But it's a very standard convention at this point, so this is, while it's arbitrary, and people sometimes confuse arbitrary with meaningless, is not true. Right? We have to be on board with how planet Earth does business, and this is how planet Earth does business. So notice on this part of the boundary curve, this direction along the boundary, if you were walking along that way, that's the way that you would go that would put the region on your left. If you were going the other direction, the region would be on your right, not on your left. Does that make sense? So that's the convention, and notice most of the time that does conveniently mean counterclockwise. Most of the time, not always. Good exercise to think through for yourself. For a little interior piece of boundary like this, like imagine if our grassy field had like there was a pond in the middle of the grassy field, you would have to walk clockwise around the boundary of the pond to put the region, the boundary, the grassy region whose boundary you're talking about on your left. So don't make the mistake of thinking that the rule is counterclockwise. It's not true. It's always such that the region is on your left. Okay, sorry I went a bit over. We'll draw the line right here, and we will do exciting stuff on Wednesday. See you later.